thanks for coming. Today I'm going to talk about ephemeral Hadoop clusters in the cloud. So, I'm Greg. I'm an engineer at Etsy. I work on the Data Wranglers team, which is our team for using big data to build products and for internal tools and things like that. So, Etsy is the world's handmade marketplace. It's a site you can go to and people go on there to buy and sell handmade goods, vintage goods, and supplies. Here's some stats on Etsy. We have about 9 million members, 800,000 active shops that sell things through Etsy. A little bit less than 10 million items are for sale on the site right now. Over 1 billion page views per month, and in 2010 we had about $315 million of gross merchandise sales that happened on Etsy. So you can guess it's a pretty active site. There's a lot of things going on, and with that comes lots of data for us to analyze. So the goal of this talk is to tell you about our story, how we kind of came to use Hadoop. And it's a little bit unorthodox, so I hope that there'll be something you can get out of it and see how we actually adapted towards using it to analyze our data at Etsy. So in the title of the talk, I used the word ephemeral, and I guess I want to just convey what I mean by that. And so what Etsy does is whenever we run a Hadoop job at Etsy, we actually build up and tear down an entire Hadoop cluster each time on Amazon using elastic MapReduce. And so that means that when you look at the end result, there's absolutely nothing running. The cluster is just there to do its work, and then it's completely gone. So I kind of likened it to a sandcastle that you build up, and then the ocean comes and washes it away, and there's no trace of what was there when it's over. So I mean, sometimes even at Etsy, instead of referring to it as the cloud, we refer to it as the beach, because it's kind of this shared pool of resources that you then can just see be gone when you're finished with it. So I think it's kind of like elastic to the extreme. I think, if you have an elastic system, often you'll have some baseline level of hardware you're using, and you kind of use the elasticity to add capacity and take it away. Whereas in this case, you're kind of taking that to the extreme, where when there's nothing needed, there's nothing there, and it's completely gone. So here's a graph that I wanted to show you guys. It's showing our node usage over time. And I think there's two interesting things to notice about it. The first is that it's obviously cyclical, because we have a big job that we run every day that analyzes the previous day's data. I think that's pretty common. But the other interesting thing is that there are these gaps in the graph, towards Sunday there, and those aren't missing data points. That actually was when everything was shut off, where we actually had nothing happening because there was no work to actually be done. And this is a graph of our total dollar usage per hour. And again, it has this cyclical structure where at some points we're using almost $300 an hour for a very short period of time. And then it goes all the way to zero at certain points of the day. And here's the number of jobs we're running at any given time. And again, when I say we're running a job, that means we're actually running a unique Hadoop cluster running that job. So again, it's kind of cyclical and it has low points and sometimes goes all the way to zero. So how did we get to this scenario where we're actually building up and tearing down these clusters for elastic MapReduce? And I kind of just want to go through the thinking process and what led us to this approach. So it all began when we wanted to start to dip our toes into this big data stuff. And I think it's probably common that the problem you need to solve is taking load off your database, not grepping your log files anymore because they're getting too big. And that was the same case here. I mean, we had a data warehousing type setup where we were loading data into a separate database, and we wanted to be able to do a better job of not having to do joins on that database and things like that. So we looked at Hadoop as a way to start doing that offline in the cloud. So Etsy really has two primary data sources that we use for this type of analysis. And both of these data sources first needed to get moved onto S3 before you can analyze them on EC2. So the first data source we have are our database snapshots. And we built a really simple tool that just shuttles this data in nightly diffs onto S3. And so every night we pull a diff of each table of the rows that have changed by looking at timestamps. And then we run a Hadoop job that basically merges those records together on their primary key. And the result is that at the end of every day, you have a cohesive snapshot of each of these tables. And of course, you can rebuild these if things change or things like that pretty easily. But this is kind of our first primary data source that gives us access to our database tables in a way that is accessible to MapReduce. Additionally, we have our visit logs. And traditionally, these would be your access logs to your web server. However, we've actually instrumented things a little bit differently on Etsy where we have Akamai serve up event beacons on the site. So whenever you hit a page on Etsy or you do an AJAX call, we actually fire one of these event beacons as a pixel that has all the parameters about what occurred, and that ends up going into an Akamai access log. And so we strictly analyze those logs since they're meant to be one-to-one with our PHP Apache logs as well. So we have a Hadoop job that basically goes through, takes these access logs every night, and the output of that job is a simple tuple that has as its key a visit identifier, which is basically a session key, and then a list of all the events that occurred. And the events have the type of event, and then all the different properties that were fired with the pixel at that time as well. So now we have our two data sources on S3. We're ready to start playing with it with Elastic MapReduce. And we realized we needed something that was like a series of tubes, something that we could use to do kind of traditional relational operators on. And so, we needed to be able to do joins and group bys and filters and merges and things like that. And so we looked at a few different projects. I'm sure you guys are all familiar with some of them, like Pig and Hive. And so the project we ended up going with was cascading. And so cascading, if you don't know anything about it, is a way to model these kind of data flow processes in a higher level abstraction than MapReduce, where you can say things like join and group by, and then cascading will actually generate a MapReduce job for you by analyzing the graph structure of your data flow and breaking it up into map and reduce stadiums. So we really liked cascading. We thought it had a really great implementation. There was a lot of deep thinking that went into generating these MapReduce jobs efficiently, and it had great support for all the data formats we wanted to use. But unfortunately, since it's this nice data flow that you want to describe, we really didn't like the fact that it had this kind of clunky Java syntax we had to fit into. I mean, data flows generally have a very hierarchical structure, and things are merging and branching and things like that. And we really didn't feel Java provided a good way to describe these things. You kind of have to have this imperative plugin where you're plugging things together imperatively in Java. And so we wanted to figure out a better way to do that. So we came across this project called Cascading JRuby. And this was a simple JRuby layer over the Cascading API. And so it actually started outside of Etsy, but we've kind of taken it under our wing, and we've really shored it up a lot over the last year and a half. And it's already open sourced on GitHub, and we have a really good blog post about it as well, if you guys are interested. And so I'd like to just give you a high-level view of kind of what that looks like. So as you can see, it's kind of straightforward-looking Ruby code. And I think I want you to take away at a high level kind of just the aesthetics, how you get this nice nesting structure, and you can see a little bit more of the structure behind these data flows, as opposed to if it was just a flat, imperative series of lines of code. And so what we're doing here is you can kind of read it from the top down. So we're tapping a database snapshot, and that database snapshot is a listings table, which is basically the table that contains every item on Etsy that's listed. So then we create a concept called an assembly, and that is a kind of unit of work that Cascading is going to use to generate a MapReduce job around. And so the goal of this assembly is to basically go through all the listings. On Etsy, you can tag your listings with words that are useful to search by. So we're going to take all the tags off that listing, and then we're going to create a branch in the flow that goes off to the side that groups by that tag, each tag, and then counts them. And then finally at the bottom, we're going to sync that output. And so the ultimate result is that you read from S3 the listing data, it's processed in this MapReduce job, and then the output is an output on S3 that has each tag that appeared at least once in all the listings and a count. And so it's really nice to have this Ruby syntax, and of course all the metaprogramming facilities you're used to in Ruby for building these data flows kind of in a more intuitive way, both in terms of building them and also expressing them in the code. So basically our flow at this point was we would take our job that we wrote in Cascading JRuby, push it to S3, and then we would go on and run Elastic MapReduce from the command line. And what that does is it starts the cluster, runs the job, and the output is saved to S3, and then this cluster is shut down for us by Elastic MapReduce. And then whenever we needed it, we could just go access it on S3. So this was a good setup for doing these ad hoc kind of analysis jobs. Now we wanted to take it a step forward and try to start building a product around this toolchain we started with. And so on Etsy, you can go around the site and you can favorite items that you like. And so what we wanted to do was build something simple that would allow us to recommend shops that you might like on the site. And so it was this shop recommendations project. So we kind of saw this happening in 3 steps. The first steps would be to use the cascading stuff we had already built to take the data from favorites and users and just join it together into a form that can be used. The next two steps would be kind of your classic machine learning problem, where you need to train something on that data and then use that output from that training stage to predict something. So we call that our analysis and our prediction stages. But we still didn't know what we were going to do for that. So we looked around and we actually had some expertise in-house for a particular algorithm to do this, and it's a little bit technical, but it's called a singular value decomposition that does some analysis on the input data to make predictions against it. And we looked around, and the in-house experience we had, combined with the very few options we had to choose a good implementation, led us to MATLAB, which is a scientific computing package that does this type of algorithm pretty well and efficiently. So, now the world looked like this. We had this first step with cascading that was very clear, but now we wanted to have MATLAB actually do this training phase where we load all the data in memory, do this SVD decomposition, and then use that output to do these predictions. So you might be wondering, right? So the goal here was to try to get this to work. So we went and we had our cascading stuff, we put it aside, and now we wanted to get MATLAB to work. So there's a project called Hadoop Streaming that I can give you a quick overview about. And what it lets you do is it lets you have arbitrary scripts for map and reduce. So it's a very simple contract. Your data gets sent in on standard in, and you have the ability to write an arbitrary script for map, an arbitrary script for reduce, and then you write your output on standard out as a TSV. And so this kind of gives you a lever to do pretty much anything you want with the inputs and outputs, or anything in the middle as well. So this kind of turned into this Swiss Army knife for us. Traditionally you'd think it was just a way to write map and reduce tasks, but we actually figured out ways to use it as a way to do all kinds of other things that had side effects as well. For example, if you ever wanted to analyze the entire data set, we would actually use this as a way to run a single reducer node and load all the data onto that single reducer node, do some type of global analysis, and then move on. And that was exactly what we needed for this MATLAB process. Additionally, we could also use it to generate secondary artifacts. So you may use it to generate a Tokyo cabinet file or a Lucene index or a SQLite file along the way in your overall MapReduce job. Additionally, we could also have kind of crazy side effects like create some schema on a MySQL database and load data there, or push data out to CloudFront to be published to the web, all in line as part of a kind of single Hadoop task. So now we thought we had a plan. We could basically use Hadoop streaming to run this MATLAB stuff in this chain of three steps. So first step, you prepare the data with cascading, you do a big one-time in-memory preparation of it in MATLAB to train the learning model, and then you predict with MATLAB kind of in parallel after that. So now we need a way to chain these guys together. Now these three things are going to run on totally separate clusters, and we needed a way to spin those things up, set them down, and have them be able to talk to each other one by one. So we have a project called Barnum that we built that's basically a simple scheduler for doing this kind of stuff with Elastic MapReduce. It's a Sinatra web service on EC2, and the way that it works is Barnum will start a job and spin up a cluster, and then it gives the cluster a callback URL to call when it's finished, and that calls Barnum back again, and then Barnum will know what to do next. So I'll step through a really simple example. So we're running Barnum on this node right here, and it's a Sinatra service. A user comes in, or a cron job comes in, tells Barnum run this task. Barnum then looks for the first job to run the task, starts an EMR client to call the API, and that starts a Hadoop cluster. The Hadoop cluster runs, does its work, and then when it's shutting down, it calls Barnum again, saying, I'm done with this job, do whatever it is you need to do next. Barnum starts the EMR client again, and then the old cluster is now shut down, and Barnum then starts the next cluster after that to do the next job. And they can have completely different configurations. So Barnum provides a few different constructs for kind of building these flows above the cluster level. So the first is the simple task. So you can wrap your job with a task to run it in Barnum. And in this case, we have a task with a single job. It's a cascading job, and it runs 45 C1 medium. So it's a moderately sized cluster. And then you can just run that job as itself, and the task starts and finishes with that job. Secondary to that, you can chain things together. And that's kind of what I was talking about with our project here of recommended shops, where we want to chain these jobs in sequence. So it will run job B, and then once job B is finished, it will start up a new cluster for job C, and then only when that is finished is the task finally finished. The third case is when you actually want to have a little bit more complex dependencies between jobs. So we call that batching. So in this case, you might want to run job D and job E on separate clusters, separate configurations and environments, and then only run job F once both of those have finished. So whichever job is the last one to finish causes job F to start running. And finally, we actually have a construct you can have above tasks where you can branch tasks. So when a certain task as a whole finishes, you can kick off multiple tasks from there. So from all these constructs, you can imagine there's a lot of kind of interesting things you can build on top of all these clusters being spun up and spun down. So back to the project here. So we basically needed to build this chain of these 3 jobs running. And the first would be cascading, the second and third would be MATLAB. And they would have wildly different configurations and be running wildly different bits of software as well. So I'd like to go through an example and kind of show you how it looks for us when we build these things and how Barnum goes through the actual process itself. So on the left is a YAML file that is the descriptor we use and we give Barnum to describe what it is that we have to do. And it's broken up into 3 sections. The top section is a schedule, and that's just basically a cron tab if we want Barnum to run it on a schedule. The second section is the transitions table, and that basically describes what steps to take after each step. So each of those keys there is either an initial state or a state in the transition table, and the value there is what to do on either a success or a failure. And at the very bottom you can see it says done, that's when the whole task is finished. And the third section are the parameters to pass to those different jobs when they start up. So there's kind of a common section there, and those are just paths on S3 we want to share across all 3 jobs. And then each of the individual jobs has a section describing the machine type to use, the number of nodes to use, and then additionally a few of them have user-defined parameters that the job itself might need to know how to run. On the right, you can see kind of the top there where we start with our 2 database snapshots, one of our users table and one of our favorites table. And again, as I mentioned, these things are kind of being regularly saved to S3 using our nightly tool to take differentials out of our tables. So when Barnum is asked to run this task, it first goes to the transition table and looks up the start key, figures out what it needs to do. So it realizes it has to run the join favorites job, and that's again the first step here. And it sees that it's a cascading job. It takes 20 C1 mediums, and it has a parameter passed in min listings equals to 3. And so it starts up 20 C1 mediums on EC2 to run, represented by those little circles there. And it runs the job, and then the output of that job is saved out to S3 as some join favorite data. So that's the data we're going to use to analyze in MATLAB to actually make the recommendations. So we've kind of done this database join now on the cloud using this cluster. So that's finished, so now those nodes shut off. And right before the master node goes out, it calls back to Barnum to do the next thing. So Barnum looks in the task file, it's told what just finished, looks in the transition table and sees analysis needs to run. So analysis is completely different in nature. It runs on a single node, M2-4X large with a lot of RAM, and it runs MATLAB. And so the idea here is now all that data from that join favorite data, after it starts the one big node, gets pulled in and analyzed by MATLAB over the course of an hour or 2 sometimes. And the output of that is a large MATLAB bin file, which is kind of an artifact of that analysis, this SVD decomposition that it does. So then finally, once that's finished, and the nodes process all the data, it shuts down, the bin files have been saved to S3, and the cycle continues where Barnum is called, it looks up in the table, and analysis ran, and now it runs the third task, which is prediction. And prediction is a streaming job as well, also running MATLAB, but instead of being run on a single node, it's actually run in parallel on, in this case, 10 nodes. And so each of those 10 nodes takes the artifact file from the previous step, runs the prediction for all the users through it, and the output gets sent to S3, and then these are ultimately our predictions for the shop favorites. And so finally the cluster shuts down, and our main artifact is sitting on S3, our predictions. And you can see as things go, we only use the computing power we need, and each cluster is shut down as soon as it can be, but the ultimate result is you have this nice chain happen where you can have all these different characteristics be used throughout. So now we had our data getting generated with the push of a button on S3. So we need to figure out a way to get the data back to our data center to use it for this product. So this is kind of what version 1 looked like. It was a little bit of a mess. It was kind of duct taped together. It was a bunch of ad hoc shell scripts. We were passing like TSV files around. and loading it into a dedicated MySQL cluster or node, really. And it wasn't something we really could reuse. It was just something set up so that we could get this stuff working. So eventually, once we started building more Hadoop jobs, we wanted to come up with a better way that could be reused. So version 2 looks like this. So the last Hadoop cluster to run in a given task, will save the final output to S3, and then it crosses the data center barrier there to call an API on Etsy side, notifying us that the job has completed, the whole task has completed. So this doesn't actually happen until the task as a whole is finished. So on our side, we actually have a pretty nice Gearman infrastructure running. So once that's finished, we spin up a Gearman job or two that will basically take the data from S3 and then load it into MySQL, and then optionally load it into Memcache and heat up the Memcache records for that data. So one thing to note here is that when we load this data, we actually create a new table each time. So when you generate a data set for Monday, we actually generate a new sharded MySQL table for Monday for that data set and do the bulk insert each time. Additionally, we can also warm up the Memcache stuff so that when this product goes live, there's no cache misses happening. When we run a job, the data sets are versioned based upon when the job was run. And those ultimately end up being how we name the tables that we end up generating inside of our Gearman job. This is our console on one of our internal tools that kind of shows you how you can actually manually queue these up if you like, or you can see the historical runs that have happened. So these are about 7 or 8 different data sets that have run, their timestamps and their version numbers, and the status of the load. So the load can go from it's either loading it, or it's warming up the cache, or it's finally available. And so it's not until it's completely available that that version of that data set is available to the web stack. This is a snapshot of the tables you can see if you look at our MySQL node. So you can see there's actually a new table each night for this particular data set. And then again, here's a graph in Ganglia of our Memcache nodes that we have for this getting loaded up every night with new data. This is a graph of the set rate. So the way we model this in our code is we take a data set as a whole and we model it one-to-one with an ORM model. We have an internal ORM at Etsy that we built. And so we basically built this on top of that so that we could access these data sets. So the way that you start with this is you write a PHP class, right? And the only difference is that you inherit from this dataset row base subclass or a base class, and that gives you all the functionality to access these data sets. Now on the cascading side, all you need to do is wrap your output. So you kind of branch your output in the data flow with this dataset construct, and you have to just clean it up a little bit on the way out. But the idea is that when you do that, it does two things. It outputs the data to S3 in a kind of canonical place, and it also outputs it as like a JSON gzip file. So basically now our Gearman job will know how to load it. So once Barnum is finished running that task, it knows that this job had this data set registered with it, and it actually will call the Etsy API to queue up the load for that data set. And then for the consumers of this, all they need to do is basically, before they start accessing the data through these ORM models, they just call a tap function. And what that does is that goes in and it looks to find the latest version of the data set that was loaded, and then basically binds the ORM model to those tables. So if it was last run on Monday, it will bind the table to Monday. But if it was last run like 5 days ago, it will bind that ORM model to the latest table that was available. And of course, we regularly drop these old tables. So the motivation behind this is just simply to make it so that we can have data be not quite finished loading yet, and then we can kind of in a single shot atomically make it available, and at the same time make it easy for us to drop the old data in a way that it's not going to end up causing defragmentation or things like that. So we're using this stack in 2 ways. That's kind of the whole stack as a whole. So we use it internally for analytics, and we use it externally to build products on top of it, like that suggested shop stuff I was talking about. So analytics, it's pretty straightforward. We have a dashboard where you can see tons and tons of metrics on how people are using the site on a regular basis, and that kind of gets drawn out of those visit logs I mentioned that we aggregate every night. And then we're also playing around with some more interactive tools. This is a screenshot of a tool called Tableau. We're experimenting with using this as a way to do ad hoc segment analysis on the data once it's been kind of cleaned up by Hadoop. But more importantly, we use this to build really cool products. So here's some examples. So we have a product called the Etsy Taste Test, and what that is, it's something that people can go to, and we give them a grid of like 6 items, and they choose the one they like the most, and they keep doing that until we have a certain amount of confidence, and then we generate a whole bunch of items for them. And so behind that is a whole bunch of data sets we load every night to make that possible. We have another tool that's really cool. It lets you shop for people that are your friends on Facebook. And then what happens is we look at their interests, and then we use their interests combined with search query logs to make good recommendations of items on Etsy that match their interests. And then again, like I mentioned, we have this suggested shops tool on your profile that you can go to see shops you might like. And that again is behind the scenes running these MATLAB jobs to generate these suggestions. We're also using this stuff to improve search quality as a whole and figure out better ways to recommend things to people on the site. So to kind of be a testament to the effectiveness of this, again, we didn't really start out this way thinking it was going to end up here, but in May we ran almost 5,000 of these. So that means we built up and tore down about 5,000 distinct Hadoop clusters without any problems. So I think it's a real kind of good data point to show that, at least right now, this approach is working really well for us. But I would like to make sure I take time to talk about this sandcastle idea. And I think, the nuts and bolts are interesting, but the thing that is really kind of compelling for us is just how this has changed the way we work with these types of problems, and also the things that we've not had to learn because some of the stuff has just been taken care of for us. So the first thing is that by having this like extreme elasticity, we've kind of been able to build this system up iteratively from the very beginning at 0. So we didn't have any upfront investment into building some end-node cluster, and we were able to tackle really hard problems with large clusters from the very beginning at a very minimal cost. And it gave us this really nice playground to start learning about Hadoop in and be able to solve problems with it that actually warranted using Hadoop. And often, to really have a good problem, you need access to the hardware to solve it. And this gave us a way to start learning this stuff in a really realistic environment. Having these clusters run like this, though, also has provided us with, I think, 2 really good forms of isolation. So there's isolations across runs. So basically, as I mentioned, we build up and tear down every node every single time. So, if you get something working on a node, there's a pretty slim chance that things like environment or installed libraries or things like that are going to burn you because every single time it's a clean slate. I realize there's like configuration management tools and things like that help, but in our case, that entire problem kind of just goes away because we just have a clean node every single time. But I think more important than that is we have complete isolation between developers. I usually have no idea what other developers are running on our Hadoop stuff because they get completely dedicated hardware resources. So somebody might be running an experiment where they run 500 nodes and nobody else even has to know about it because it's in its own little environment. So there's nobody stepping on each other's toes, and more importantly, nobody's stepping on a production system, right? Everything is separate. So that's really nice. It also gives us this nice heterogeneous cluster thing, so we can kind of optimize for different use cases. For example, if we need a lot of memory, then we can spin up a big node and get all that RAM. But we only use it for the time that we need it for. So for the example of the MATLAB stuff, we might build this giant matrix in like 7 or 8 gigabytes of RAM, but we only pay like $3 because we used it for like an hour. So you don't use it when you don't need it. It's not sitting there idle. But then also, the whole process of writing a job, I think is like dramatically changed when you have this capability at your fingertips. It kind of gives you these phenomenal cosmic powers. You kind of realize, wow, if I have an idea, I have access to, all this infrastructure. For example, if you're prototyping something, you often don't have the right solution right away, and you often will have a solution that's really slow or unoptimized. But you really don't know if it's worth the time to invest speeding it up. Like, you really want to get down in the dirt and optimize your map reuse jobs before you even know if it's going anywhere. And so for in this situation, you can actually run this thing on 500 nodes for less than $100 to disprove or prove your hypothesis that this approach you're taking makes any sense. In fact, often we'll have jobs that have a number of different tuning parameters. Like, you may have some cutoff threshold for the number of items you want to look at, or you may have some machine learning model that you are tuning the cutoffs for and things like that. And so what this allows you to do is, instead of having to guess or to wait for it to find these things, you can actually kick off a one-time big cost up front and try every single combination of them that you think is interesting, and then you get your answer in kind of a constant time. This is all running in parallel. So again, it's like all these big fixed upfront costs that you make, but it really ends up saving you all this effort in the long run. So I think it kind of gives me the feeling of awe that I had when I first learned how to code or things like that. It's kind of giving you this amazing tool at your fingertips that I think, for us, it's kind of something that's actually genuinely new. It's something that, expands your ability as a developer. And so I think that's why I wanted to give this talk, and I hope that you guys enjoyed it and take any questions. Sure.
From an Amazon machine perspective, are you reserving instances, or how is that working? Is it just requesting new machines every time?
Right, so he was asking if we're using reserved stuff or just on demand. So we're using just on demand. I'm actually not even sure if EMR supports the reserved stuff. They might now. But one thing is that we've really not spent much time optimizing on cost. And in my original abstract for this talk, I was going to try to talk about cost, but retrospectively, I think we just haven't even tried to optimize it. So I didn't feel like I could make a strong case either way because we don't even know where we could end up with it. But in that sense, that would be the type of thing we would use to optimize cost, I would guess, is to try to reserve stuff smartly. Sure.
So is there any plan to extend Barnum to actually use the cluster within the whole job? For instance, you have
right.
jobs in the Barnum. And the reason I ask this is because obviously there is some time that you use the whole execute bootstrap actions and everything like that.
Right. Right now, we haven't really tried to do that. I mean, I guess you're working against a few things, right? You have, like you said, you have this kind of constant startup time, and then beyond that, another kind of common catch point, I think, is Amazon rounds up to the nearest hour, so there's kind of that residual time that you might be paying for that you didn't actually use, so the reuse could help you there. In practice, I mean, it hasn't really seemed to us that is a huge win, but we do support having, for example, running it and leaving the cluster up for debugging purposes, but we haven't made it so that we can go back and reuse that cluster for other jobs. But I don't think it would be too hard to do that. Sure.
Has this gotten folks who aren't on the development team more involved in wanting to run experiments and stuff like that? It just sounds like it opens up an opportunity to do a lot more, even if you're not on the development team.
Right. So I think, so he was asking if people outside the development team have been able to get more access to Hadoop than otherwise because of this stuff. I think what we found is it's still really hard to get people outside the development team. However, one thing we've noticed is that we've started to actually move this stuff outside of our own little data scientist type of team into other areas of the organization, and they've been able to run with it. For example, we're using it now to kind of power a lot more kind of sophisticated search algorithms, and so our search team at Etsy is well trained on this stuff now, and they've been able to run with it. And it kind of also tacks back to that point I made about developer isolation. These guys haven't been able to run with it, and we really don't even know how much, I mean, the powers that be know how much money they're spending, but we don't know that, it doesn't affect me that so-and-so is running some job about search relevancy and analyzing search queries. I'm just not aware of it, which is I think really helpful to getting that to spread out without it causing conflict.
Sure. I was curious about your use of MATLAB. I was wondering if that came out of prior experience, or did you just do any sort of shopping around saying what's the best SVD library, etc.? How did that play into your framework?
Sure. So he was asking what made MATLAB be our choice for this thing. So partially it was past experience. So one of my colleagues, Stefan Karpinski, he has a lot of experience with MATLAB and this type of algorithm. However, the particular implementation requires a sparse matrix representation and doing SVN on that. And so I think there's relatively few of those that actually work. I mean, there's I don't know, I think there's some that are in C++, I think Pack might have one. But in practice, Stefan came to Etsy with a whole bag full of MATLAB scripts, and basically that combined with the fact that we knew that it was a hard problem, that we wouldn't just be able to pull some off-the-shelf open source thing to do, led us to try to get this to work. And it kind of had all these other derivative benefits, because we felt like once we got MATLAB to work, we could get anything to work. So then we were able to kind of use it for other things as well. Sure.
So I have a kind of general question, which is Given this stack, where does your development team spend its time? And to clarify a little, I mean, if I were running my own Hadoop cluster, I'd worry a lot about cluster configuration, kicking the hardware when it goes down, that kind of thing.
Yeah.
Given that your stack solves some of those major problems, my question is, what's the new benefit? Like, where does your development team's time go now in the contract?
Sure. So I think, let me think about that. So the question is like, where do we spend our time? And I think it's really important to note that I don't think that I'm a Hadoop expert because I haven't had to like dig into a lot of the horrible things I hear that sometimes people have to deal with it. So I think, but we do run into a lot of kind of things all the time. I mean, a classic example is where we write these really sophisticated jobs, but then when we run them, we find that they take really, really long because all of our data gets crunched down to a single reducer and because of these like long-tail distribution type things. So that's like a common thing where you have to like retune these things. A lot of the time that we do, actually, that I think is a function of this approach is we spend a lot of time dealing with data shuttling. Like we have more kind of moving parts involved to make sure the data that was logged on Akamai actually gets to where it needs to be correctly and verifying that and that kind of stuff. I don't know, Matt here is also from that. So do you have anything to add, Matt?
I spend a lot of my time actually building out and using the analytics side that we didn't talk about as much here. And so, I mean, the spike in jobs each night is about 50 analytics jobs running a night, and which 50 those are changes every night. So, I mean, we're doing a variety of analyses all the time that, either, like he showed charting, but we also do A/B analysis, and deeper sort of ad hoc analysis and stuff like that.
These are analytics jobs that might run on like the MATLAB output.
No, in this case, they're pure cascading jobs.
Okay.
Yeah. So, and I guess another point is that some of the as far as leaving a cluster up and utilizing it more than just for one particular job, cascading internally can be very elaborate. So the algorithm behind the Facebook gift recommender is actually a single monolithic cascading job, but it has many flows in it. So this is like, it really utilizes one cluster. We put it on 100 large machines, and it runs for like 6 hours or whatever. So, yeah, I mean, there's different people are doing completely different things with this stack.
Yeah, I mean, we've not really lived in a world without it, but I would wager that we do spend probably more percentage of our time building actual stuff. I would hope, but it's hard to say. Sure.
Can you speak to some of the specific challenges of shipping your data into S3 and the major alternative to HDFS?
Right. So I think, Matt has done a lot of battling with just the Akamai side of things. I think, Akamai doesn't really have any strict hard SLA on their logs. And so we kind of learned that the hard way that, there's going to be latency on things. I mean, one thing that has been a big pain is that for us to actually be confident that our visit logs are actually correct for a certain day, we have to wait probably longer than you normally would have to wait because we have to be sure that they've all showed up on Akamai's side. Beyond that, there's a lot of kind of checksumming we do. Like when we upload something, we always download it back from S3 and just checksum it just to make sure that nothing was lost in translation.
From past experience.
Yeah, from past experience. We actually did, and if any Amazon people are here, they might disagree, but I have seen S3 swallow a file, and so that happened once, but you got to deal with it. Yeah, so just lots of like little things. Also, our database snapshots. Occasionally, like when people migrate schemas, we have to like coordinate with them so we know that the snapshot is not going to break when they migrate the schema and things like that. So that's another thing. Sure.
Is there any plan to wait till Windows running?
We've talked about it. We've talked about it a little bit. I kind of glossed over a lot of the kind of fancier features we have in Barnum, and it's hard to know how much those would be really useful to the outside. So we've talked about it. I think there's going to be a good amount of work we need to do before that will happen, but it's definitely something we'll consider.
And between the US and the USC, so there's really referred for jobs.
Honestly, like all of our S3 buckets were created in East when we started, so we've always just run on East. We're not running like this stuff's not plugged in like live, and no users are hitting it, so we're not really thinking too much about the topography and things like that. Thanks, guys.